Okay, so we're solving polynomials that have complex solutions, and in particular, like I've just said a minute ago, we're solving quadratics with real coefficients. We'll get into the harder stuff in Unit 3. So recall these facts. A quadratic could have 0, 1 or 2 roots or solutions or zeros in the real numbers. In the complex plane, there are 2 solutions or possibly a double root. So there could be just that one double solution. That still exists. So formally we talked about the determinant. This is term 4 last year in year 10. You talked about the fact that if the determinant, which is the bit in the square root sign of the quadratic formula, was less than 0 or greater than 0, there were 2 real solutions. Equals 0, there's one solution, it's a double root. And if it's less than 0, there are no solutions. Now we know that if it's less than 0, we can now square root that number. We just end up with a complex solution. So it's this group here where we generate now complex solutions. So here's an example. If the determinant is -9, we would have formally said, and in math, just keep this in mind, complex numbers are not in math methods. So if you get a question that's a quadratic that has a determinant of -9 in math methods, you aren't expected to solve it. That's the bit where you say there are no real solutions. But in specialist maths, we expect you to recognise that there are complex solutions and write those down. So the square root of the determinant is part of the quadratic formula. The square root of -9 is the square root of 9 times the square root of -1, which is 3 root I. Oh, sorry, 3I, 3 root -1. Any questions on that? That's basically what we're doing today. What I'm going to show you now is some examples where we use a quadratic formula. It'll be trivial like that. And then I'll show you some examples where we complete the square or where we use these skills to factorise over the complex numbers. So example 1, solve using the quadratic formula. They're not actually equations, so you can't solve them. Let's write it as this. There we go. Solve using a quadratic formula. Now, I wrote these a while ago. I'm assuming they work, but they should probably give us complex solutions. So keep that in mind. So here, for A, the quadratic formula is that Z is equal to -b plus or minus the square root of b squared minus 4ac over 2a. And in this case, b is equal to 2, a is equal to 1, and c is equal to 10. And so we get z is equal to -2 plus or minus the square root of 2 squared minus 4 times 1 times 10 all over 2. And that is -2 plus or minus the square root of 4 minus 40 is -36 over 2. And this gives us some reasonably nice solutions. -2 plus or minus the square root of 36 is 6 times the square root of -i. It becomes 6i over 2. And we get -1 plus or minus 3i. Or we could write that down as -1 plus 3i, or -1 minus 3i. Okay, now what do you notice about the solutions to this?
They're complex.
Yes, they're complex, good.
They still follow the form a plus bi.
They do, and the complex numbers should always follow that form, because if you square the b part to change it, the I squared becomes then a real number, and we can transfer that across. There's something we learned earlier, that these two are a matching pair in this way. They're what, sir? They are the complex conjugate of each other. So let's just make that note very quickly. So if you put numbers into here, and the square root becomes the square root of a negative, this will be the bit that turns into your complex number. You're going to end up with the real part plus or minus the complex part. And that's what that's the definition of a complex conjugate. So we've got the real part plus the imaginary part, or the real part minus the imaginary part, every single time. That will give us complex conjugates. So a quadratic, where the determinant is less than 0, will give us 2 complex solutions, and one will be the conjugate of the other. every time because of the form of the quadratic formula. Now that changes, and this is where you have to be careful in Unit 3 and 4. That changes if the coefficients, so when I say coefficients I mean A, B and C, if they aren't real numbers. Because you could get complex coefficients now as well. If you're putting complex numbers into the quadratic formula, then you might end up with complex numbers at the front and real numbers at the back end or something else. So the conjugate thing doesn't work anymore. It's only true if you have real coefficients, which luckily for you guys in the exam you've got coming up and in the work that you're doing in Unit 2, it will only be real coefficients. Okay? So we should get complex conjugates every time, which means if you get a question in your exam, this could be a good multiple choice question. You walk in the exam, first multiple choice question says 1 minus 2i is a root to this quadratic equation. What is the second root? 1 plus 2i. Job done. Move on. Because you know the complex conjugates of the two roots. Okay? And if you get to expansion, you'll see that that works as well. Let's look at question B. 5z squared minus z plus 5. Z is equal to negative b, which is negative 1, plus or minus the square root of negative 1 squared minus 4 times 5, all over 2 times 5. And this becomes 1 plus or minus the square root of 1 minus 100. Negative 99 over 10, which becomes 1/10 plus or minus. Now negative 99 is the square root of 99 times I, and the square root of 99, that can be divided by 9. 9 times 11, so it gives us 3 root 11. So I get 3 root 11 I over 10, and that's really the best I can do. Now you'll notice here that mathematical notation or conventions would denote that we have 3 root 11 with the number first and then I. Typically that's how you do it. It's not really as common to see 3i root 11, so just be aware of that. The I is kind of treated like a variable. It's just put on the end like you would with an x. But otherwise that's it. That's our solution to that one. Not as nice as the first one, but I think I did that deliberately. Any questions? Easy? Alternatively, you could solve by completing the square. This is for you, Dylan. So let's have a look at some solutions where you complete the square. And so just be careful. There are some special cases. The quadratic formula is it's a bit of a pain, and it's also a trap. So many students make numerical mistakes in a quadratic formula that it becomes a trap. It's not on your formula sheet. It's easy to muck up writing it down, etc. So if you get the opportunity, do it in different ways. First of all, question A does not have a linear term. It has a quadratic term and a constant term, doesn't have a linear term, and it leads to this. A, z squared plus 9 equals 0, z squared equals negative 9, z equals the square root of negative 9 plus or minus, and that equals plus or minus 3i. No linear term, it's actually really easy. So just keep that in mind. Look for those little tricks. And the same thing goes for a no constant term, by the way. I haven't got an example of this, but if I just say here, no linear term, let's take the capital out of that, is easy. No constant term is also easy because that would give us z squared plus, say, 5z equals 0, gives us z plus 5 equals 0. That's easy to solve. But you know what the thing about, yes, that's fine, James. You know the thing about the no constant term stuff is that's never going to lead to a pair of conjugates. And in actual fact, if you have a look at this, there's no way that we're going to get to a point where we're square rooting a negative number. So you will never have a set pair of complex solutions to a quadratic that has no constant term. So for now, you don't really have to worry about that. But there's little things that you can do to make your life a bit quicker. The second one, B, I'm going to do purely by completing the square. Thank you. Cheers. I might actually bring the whole thing out a bit wider to give me space. Equals 0. So completing the square, and again, there's some variations. You read it in textbooks, you read it online. People do completing the square in slightly different ways. And honestly, every year I'll get somebody come and tell me that I'm doing it wrong. And whatever, that's fine. You can tell me I'm doing it wrong. I'm doing it one way. This is the way I prefer, and I think it's also the way that's the most procedural. You can do it however you like. As long as what you're doing is effective and works, that's fine by me. So my way would be to split this up and recognise we've got z squared plus 4z, and we want this to lead to z plus 2 squared. That's our goal. Because the z plus 2 squared will give us the z squared and the 4z. It will also give us a plus 4. So I need to write down here, and this is where I might step in early days and do a plus 4 in a different colour. But because I'm adding 4, and again, you might be able to skip this step, I also need to subtract 4. And then I've also got my plus 8 equals 0. So it's kind of splitting it, and I'm putting in, you know, people will talk about it's b over 2 squared gets put there, and you can deal with that if you want to. But really it's just getting the coefficient of z, halving it, squaring it, and you've got to have that added on or subtracted. So the step you might skip, particularly because you're in specialist maths, is you just get here and go, I need to add 4 to make that. What have I got left over? 4. I don't need to write down negative 4 plus 8. I know that's 4. I had 8. I need 4 of it to go towards that complete square. I've got 4 left. That's fine. You can do that. You can do your b over 2. You can do whatever you like. So I've got this plus 4. What this does, why this works, is the problem with solving up here is we've got a z squared and a z. What this does is it creates a situation where we've still got a quadratic, but z only exists in one place. So it means we can solve this quite easily now. The same way we solve question A. So we get z plus 2 squared equals negative 4. And we get z plus 2 equals the square root of negative 4, which is equal to plus or minus 2i. And therefore z is equal to negative 2 plus or minus 2i. And would you believe it? We've got 2 solutions and they're complex conjugates again. Any questions? We might ask you, and I'll say we, this is the only class, so I'm the only teacher. I might ask you to solve using completing the square. That could happen. But really, I'm not actually testing your quadratic skills at this stage. So realistically, 99% of questions is going to be solve this quadratic equation over the complex numbers, or find the complex solutions to this quadratic equation, or something like that. How you then do it is up to you. But I would encourage you to practice this because that will be, 1, almost certainly quicker, 2, probably going to lead to less chance of mistakes. So if you are good at doing this complex conjugate stuff with the completing the square, then that's probably good. Example 3, it's the last one I'll do, and then I've got a couple of little notes. So example 3, factorise z squared plus 8z plus 25. So I want to factorise that. Now, when you factorise, it means, and this is again how I set it up, and you talk to a different teacher, they do it differently, you read a textbook, they do it differently. But when I factorise, I know I'm looking for 2 numbers that add to give the b value, and if it's a monic quadratic, then I'm looking for 2 numbers that multiply to give 25. Add to give 8, multiply to give 25. Now, I look at this and I think, well, this is going to be 1 and 25 or 5 and 5. That doesn't work because none of that adds to 8. It's probably going to be a 4 plus something I, 4 minus something I situation, because we know complex conjugates work. So you could go through here and you could determine that and you go, well, this 8 gives me a 4 plus, let's call it bi, and then 4 minus bi has to be the solution. But when you multiply those two, they have to give 25. So then you could say to yourself, 4 plus bi times 4 minus bi equals 25. What's it going to be? It's going to be 16 minus b squared I squared equals 25. So you get b squared equals 9, and b equals 3, or plus or minus 3. You don't need the plus or minus 3 because we've already accounted for that there. You could do it this way. That's quite clever and that works. The other way you could do it is to recognise that once we've factorised this, so keep in mind our factors now are 4 minus 3i and 4 plus 3i. They are also the solutions. So if you go back to the factor and remainder theorem for math methods term 1, you'll remember that if you've got the factors, so z minus 4 minus 3i, then when you substitute that in, that should give you 0. So they're the solutions. So the other way, so I'm going to do, this is method 1. Method 2, which is actually more procedural and doesn't take really any logic at all, is just go, I'm just going to solve this equation. 8z plus 25 equals 0. And just to reiterate our using and completing the square, I'll do it that way, but you could do the quadratic formula. But this becomes z squared plus 8z plus 16, because half 8 is 4, 4 squared is 16. And then 25 minus 16 is 9, equals 0. That becomes z plus 4 squared plus 9 equals 0. Z plus 4 squared equals negative 9. Z plus 4 equals plus or minus 3i. Z equals negative 4. Ooh. What's that? Ooh. Negative 4. I got 4 over here. Does 4 not work? So it turns out that ultimately we just need the complex conjugates. It doesn't matter whether this is negative or positive, because once I square that out, or yeah, it shouldn't. Thanks. Over here, what did I get? Add to give 8. Oh, I don't really know why negative 4 would actually work. Don't know. Just stop that there. Might just resume this. The question says to factorise. So technically now this should mean that z squared plus 8z plus 25 is equal to z minus negative 4 plus or minus 3i, and z minus negative 4, oh sorry, that's not plus or 3, that's just minus 3i, and then this one's plus 3i. So that's the factor, and if I expand that, I get z plus 4 plus 3i, and if I expand this, I get z plus 4 minus 3i. So I think that's where the plus 4, negative 4 difference comes from. If I now expand that bracket, which will be a bit of a muck around, but some things do cancel out, I get z squared. So this is, I'll do this a bit lower because this is now, we've done the question's complete. But I get z squared plus 4z plus 3iz, and then I get plus 4z plus 16 plus, so minus 12i, and then I get plus 3iz. Oh, this should be a minus, sorry. That should be a minus. Plus 12i, and then minus 9i squared. And the 3iz and the plus 3iz cancel out. The negative 12i and the positive 12i cancel out. I've got z squared, I've got plus 8z, plus 16, and then minus 9 times I squared becomes plus 9, which gives me the z squared plus 8z plus 25. So I haven't keyed it up as much as nicely as I'd like to, but I suspect that that positive 4 is because we do the negative of a negative 4. So that's fine. So you've got options for solving these as well. And my last little thing that I'll say, as an extension, we will go in Unit 3 into solving cubics, quartics. We've talked about the complex conjugate, although that doesn't really come up in this exercise. Dealing with equations that have complex coefficients, and then we're going to talk about the complex roots of unity, which is exciting. Thanks.